Hey everybody, so this is going to be the final required Grasshopper exercise that we're going to go through. So in front of you see the outcome of the first time I did this. I'm going to go through this whole process again so you can see it. The coloring you see here is actually going to be an optional thing. If you want to go for it, you can, but it's a little bit, really you just have to get to the sort of stage that you see here, where as long as you have the structure, that's all that's really required for this, but I'm just going to show you how to add in that color, which in this case is actually representing, well, really the different lengths of these members. So theoretically, the longer the length of the member in this case, the more weight it has to carry or the more stresses would be on it. So a longer member would probably need to be potentially larger in dimension in order to take those extra stresses. So it's somewhat realistic to say that the red members actually have the least amount of stress and the blue members have the most, although I might want to reverse that relationship. You can see here, maybe I can reverse it. That's just flattening. Either way, the coloring, I'll just kind of show you how that you do that process and how you can sort of feed data into that. So if you want to get something other than the sort of standard green and or red output from Rhino, and if you want to drive those colors by something, that's sort of, I'll show you how you do that. So to start off with, we're going to need a surface. So I am just going to start by creating a 4-point surface. You can use whatever surface you like. It just should not be flat itself. So with this 4-point surface in Rhino, I'm just going to turn points on and just move these points so I can get something a little bit more unique. So maybe something like this, kind of a butterfly surface. Maybe that's going to be interesting. So I'll go with that as my input surface. So here's the script we're ultimately going to make, but I'm going to go through from scratch again on how to make that. So the first thing we're going to do is I'm going to type in srf to get a surface. Hit enter, and now I'm going to right click to set that surface. Click on that guy. So now that is loaded in. So I could hide this if I want. I'm just going to leave it. The first thing we're going to do is, since we're actually applying a pattern to a surface this time as opposed to creating a pattern on a flat plane, we need to start subdividing this surface. So I'm going to go to divide surface. Surprise, surprise. We'll put that in there, and we need to set a u and v value. So u and v you can think of as the coordinate points of an individual surface. So as when we're working in three-dimensional space, we have x, y, z, our coordinate points. A surface only actually has two because a surface is, doesn't have any thickness to it. And those are referred to as u and v. Now, whether u plus v, which is up and which is down, depending on how you look at the surface, is all dependent upon how you made the surface. So it's kind of arbitrary as to which one's which. Doesn't really matter too much. Just know that they are subdivisions. So I'm just going to do the sort of standard thing. I create a slider. Just type in 11 so I can get one that goes from 0 to 100. Plug the values into u and v. And you can see here that if I look at this surface, if I increase the v count, or the u count in this case, I can increase the subdivisions in one direction versus subdivisions in the other. I'm going to start off with a sort of small amount of subdivisions. In general, when creating things like this, because they can get fairly complex, it's good to start off with less initially and then add more once you've figured out how everything's going to work. So let's try 5 and 6. That's fine with me. Actually, I might like them if they're more square. There we go. 4 and 5. Nice small amount of subdivisions that we have there. Okay, so that's the first thing. I am going to be referencing the one that I wrote before because this one is, well, it has a few more parts. They're not really complex parts, but there are a few more of them. So the first thing we're going to do is I'm actually going to take this guy here, which is evaluate surface. So what evaluate surface is it basically allows us to get information about that surface. So I'm going to place the surface as the original one that we had. And then for UV, I'm going to use the new UVs that we've created. So essentially, subdivide surface has actually created a series of individual surfaces that is each one of these little squares. And each one has its own UV coordinates, so we're going to use that to feed into here. And from there, really what I'm after in this case is the normal direction. Normals are something I might have referred to before because they're a common thing in modeling. And basically, it's the directionality of a surface. So every surface has a sort of a top and a bottom. Both in this software and basically every software, that's how they tend to all function. So Rhino has them, like this surface that we see in Rhino by itself has a top and bottom to it. It's probably that top is facing up, but right now there's actually no way of telling. We can go to display options and enable, I think it's called backside. It's in here somewhere. Yep, backside face. And we'll just set that to, how about a single color for all backsides and make that red, just so we can see. So actually, if you look at this one, this surface is actually reversed from what I thought it was. The negative or back side of the surface is actually facing up, and down, the positive side is facing down. And that's actually kind of a good thing because that's not what I intended to do. So it will actually screw up this little definition a little bit, but because it will screw it up, I can show you how to fix it. So basically what we're going to do is we're going to create a space frame on top of this thing, and we're going to use these points as reference for that space frame. So the first thing we want to do is actually start creating the verticals of that space frame, because then we'll use that to create our second set of, so we have a bottom plane that we end up creating sort of a rectangular structure on, and then we have an elevated set on top of it. And we're going to use these normals to project that. So a normal is essentially a vector, which is a direction, but in this case, it doesn't actually have any force behind that direction. So what we're going to do is we're going to do an amplitude, which essentially takes in a vector, which in this case is our normal, and we get to define how much of a force we want behind that. So this can be plugged in as a movement now. So if we type in move, so in the past we would put a Z or an X or a Y here, but now we can just feed this amplitude into the movement, and we'll take the points from our subdivide and move them. And you can see here they move downwards. So I was intending that we would be moving upwards. It doesn't really matter, but it was how I was intending. So let's see if can we insert a flip. So we can take a surface, and it looks like we should be able to flip it. And then if we feed this in, now our movement's going the right direction. So if you ever have that problem of a surface not going the direction you want, the flip command, in this case, it's just called flip, but the one that actually has the little surface symbol on it is the way you do that. So now everything's moving upwards. So we can see here, these points are moving in relationship to the surface that they were on. So a good way to sort of understand this is actually to see what a vector is. So there's a little display here, just under display, this guy, the green one here. I'm going to plug in the vector here, and I'm actually just going to plug in points here. And now we get to see some arrows. This is not something you need to follow. It's just so you can see what they're doing. So this just shows the direction and momentum of those vectors. So you can see here they are all moving perpendicular to wherever they are on that original surface. So they're not just moving up in the z-axis, they are moving relative to that surface, which is what we want. Okay, so now we're going to do a very simple command of just do a line, the standard line that is not the param line, but the one that actually creates one that just connects between an A and a B point. So we have our A points, which are going to be our first points, and our second points, which are going to be from our move. So we're connecting these essentially elevated points that we have. So the nice thing here is, of course, we could increase the number of these lines, but I'm just going to leave it at 4. And we could also increase their length, which is just determined by the amplitude, which is how far that point is moving. So the scale here may be different for you. You know, I'm going all the way up to 100, and it's not really being that dramatic, but it just depends on how you ended up building that. It is relative to unit scale. So this model is currently in inches. So that's currently moving up 65 inches, which, you know, this is fairly dramatic for a space frame, but that's okay. Again, you know, it doesn't really matter too much for this exercise. So now what I'd like to do is actually start creating some of our framing that's going to go between these things. So we're going to do the polyline command. And I'm just going to first feed in my points and see what happens. So what's happened is they're just moving along one direction. And you can see here that all of our lines have been these sort of dash lines, which of course means that we're dealing with grafted data. So I'm just going to pull up a panel just so I can get a visual idea of what that grafted data looks like. So it looks like we have 6 points and a series of, I guess, 1, 2, 3, 4, 5 different lists, each one with 6 points. And that would be because how we divided things here. So if we were to increase one of these values, let's see if that happens. So if we increase the value here, each of the individual lists is getting longer, but the number of lists is staying the same. And then it's doing the opposite if we were to do this. So we're actually just getting more of those lists within the list. And again, grafting is inherently confusing, but that's okay. We don't need to fully understand it. We just kind of need to understand generally what it's doing. So if we do the command we've used before, which is the flip matrix, which instead of having 5 lists with 6 items in it, we'll have 6 lists with 5 items in it. And we take our list and put it there. Now I'm just going to copy this polyline command and feed it in here. We can see we're just getting the points in a different direction. So now we have our 2 grids. I'm actually going to hide the surface just so we can see what we're doing better. So we have 1 grid, 2 grids. And then we actually have our lines. So we actually already have a lot done. Where this is getting a little complicated is actually not so much in the procedure, because these things are, fairly simple operations, but we have to be fairly diligent to keep organized now, because we're going to end up with a lot of different lines. So we have our new points, which are our points that we've moved already, and we're going to do the same set of operation that we did for the first set. So I'm going to bring, and I just copy and pasted to copy that set of polyline commands that I made here. So now we have a second set of polylines and lines connecting them. So that is the majority of a space frame right there. Now we'll have to make these lines into 3-dimensional objects, because lines by themselves, are infinitely thin, so they're not really very useful for us. But what I'd like to try to do is now make some diagonal bracing going along with these. And that's where it's going to get a little trickier, because we want to connect some of our upper points and our lower points. But if we just connect them directly, we're just going to have just a series of verticals. So what I'm actually going to do is I'm going to do a command called shift list. And what that's going to do is basically, if we have 5 values, it's going to take the first value and move it to the end and move everything else up. So if I take these points in here, so I've shifted that list, and now I'm going to make a line where I'm going to use the top values as the B and my shifted list as the A. You can see here I'm starting to get some diagonals. Now I'm also getting some long ones that are not what I want, but I am getting, I think it'll be easier if we can see everything. It's starting to get a little confusing looking, but you can see that we are starting to get some of the sort of diagonal bracing that we would need. However, we need to eliminate those extra long ones. So I'm going to do a cull command, which in this case, a cull means to eliminate something. So we're going to feed our list in here. Our list is currently 42 values. Well, actually, let's look at this in the panel mode. So we have 7 values here as defined by this count. So the count is ultimately 1 plus the V. And that's just because what this is actually defining in the subdivision isn't the dots that you see, but it's actually the panels. And since we'll end up with a dot on either side of the end panel, or a point on either side of the end panel, we end up with 1 more than our original count. So we need to eliminate the last value here, because that's the one that's trying to connect back to the first one. So I'm actually just going to take my v count and plug that in here. And essentially what that's going to do is no matter how many extra points I add, it's always going to eliminate the last value here. And now I can plug this in instead into my line. So you can see here, looks like I eliminated the wrong one. You can see I eliminated something, but I didn't eliminate the one I wanted to. So I might have to do an addition. See if I need to add in one more value. I'm going to organize this in a second so it's a little easier to see, because this is the problem with a script, a definition like this is you start to get a lot of things happening. But it looks like this is working fairly well. Now we do have an extra line here, but I'm not going to worry about that right now. So let's just look at all the things we have so far. So we have essentially our space frame box. We have a diagonal running in one direction. Now, if this were a true space frame, we'd probably end up every other row would flip the direction of that diagonal. But I'm not going to worry about that too much, because that would just be a lot more of these modules pulling in and sort of organizing them to make that happen. So as long as we get them going in one direction, that's fine. But we're going to do it on both axes, which means we're going to do the same thing with flipped data. So everything that we just did, I'm going to pull apart everything now so I can make it much easier to see. So we don't need this guy anymore. That was just for demonstration, the vector thing. I'm going to pull him off. Pull all these things closer. So our amplitude, I'll put all these together. I'm going to use these little buttons here at the bottom to make some alignment, so these are easier to read. So now we basically can subdivide our surface by whatever these values are here, and then we can define the amplitude at the same time. So it's nice to keep all of your whatever these things are. Sorry, my brain is farting right now. But it's nice to keep those numbers all together. Sliders, that's what they are. And now we're going to try to organize all of our outputs. So we know that these are one of our grid directions, so we'll do that. Let's get rid of that panel. We know that we have a similar grid that I'm just going to put right below it. So each one of these I'm going to now group by selecting them and right-clicking between them and hitting the group. And this is really just going to be for my own sanity, so I can keep these things organized. So we'll put those there. We have the lines. This is the first thing we did. It just made the vertical lines, so I'll pull them up. And now we have our diagonals. So I know that I'm going to do the same thing going in the opposite direction. So all I'm going to do is actually just select these and copy and paste them and move them up. Because in order to get the other direction, what we need to do is do the shift of the list that we had done previously. Now, all these wires are starting to get a little confusing to look at. So I'm actually going to come in here and right-click and go to Wire Display and go to Faint. And essentially all that's going to do is just make it a lot easier to see. Since I don't need to adjust these things anymore, I can just go ahead and make these not... You can also go to Hidden, but I think Faint is easier because you can still figure out where they go later on. Now, if you click on something that is hidden, so if I were to click on this, it'll show it again, so it's not the end of the world. But I do prefer the Faint, so that's what that'll look like. But now it's much easier to see what's happening here. We still have a lot of wires going on. But we know we need to do the flip command in order to get going the opposite direction. That was the wrong flip. We need to do a flip matrix. And then I'm going to take points, go in here, and do that. Now, if I just do one, it's going to go all kinds of crazy and do that, which is not what we intend for. And the other thing, we're going to flip this guy and apply there. And again, I'm going to pull this apart so I can explain this a little bit better. But we also need to take this value. Okay. So essentially, we should have diagonals going in different directions. So the last things that I did here were that, so in order to get the lines going in the opposite direction, we have to take the data and we have to use the flip matrix. And that just takes the same points, and instead of organizing them by rows going this way, it will organize them by rows going the opposite way. So any data that we do that to will do that. So when we created our first set of diagonals, which we did by taking the list, one of the list, and it doesn't matter which, and then doing a shift to it. So it just shifts every unit by 1. So this point is now not going to go to the first point, it would be the last point, and this is the first point. So now they are across lists, with one being shifted and the other not, they will connect diagonally. And then we cull the one because we don't need it to go all the way across. In both cases, we're going to feed that culling by our u and v value. And we just have to figure out which one's which depending on what we're doing at the time. And we need to add 1 to it. So in each case, I just have an addition. And that ensures that in this case, we need to cull value number 6 because that's what's coming out of here. Whereas the value that it was being fed was number 5. Because this list actually has 6 values, or each one of the list in here, although there's 54 values here, there's actually 6 points on each of those values. It's just one more than the u and the v. So we cull the last one, and that allows us to make these lines. So again, I'm going to try to pull these things out so that you can see a little bit easier. But essentially the same process happens. So if you get it successfully working for one of these, the other one should work fine, just adding the flips to the points that you're pulling in. And again, we have our sort of moved points and our original points. So now, I'm going to now just do a curve. So this is the same type of curve that we use to input things, and I'm just going to drag everything in here, just so that I can select one thing and we can see them all at once. Now I need to hold shift. But you can see it building, so there's a basic space frame before we add any angle pieces in, and then our space frame with some angles. There we go. Looks perfect. So now you can see here, if we adjust the amplitude, it grows. I'm actually going to edit this guy so I can go higher. Let's make that 1,000. So a real crazy looking space frame if we were to go that high. Really unnecessary, but you know, it's an option. We can also increase the count. So we could go as low as having a few, or as high as, you know, a ton. It just depends on what you want. Again, it's good to keep it low when you're editing, and then once you have come to a definition that you're starting to like, you can go for something else. Of course, you know, this being Grasshopper, we could still come back to Rhino, turn our points back on, and since we're only dealing with lines right now, this would actually be pretty quick. You know, we're not having major issues with this slowing down. Of course, this has all my other towers and such in it right now. But you can see here, this should work for any single surface. So I'm going to try just inputting another surface just to see what happens. So actually, I'll take these. God, this random model's messy. I'm going to loft these original curves from that first exercise we did and see if it'll work. Because as long as this is a single surface, it should work okay. Which, that's an open poly surface. I think I did that wrong. I'm just going to select ungroup, and I'll try lofting one more time. So I don't know why it's only giving me straight sections. But it won't work with just straight sections. So let's try another surface. How about a fully spherical surface is going to be weird, so I don't think that would work. How about just a simple archway? There we go. Okay, simple surface. Let's just set this, and now it's applying there. Okay, so that's promising that it worked that time. But yeah, we can really stretch the dimensions here. Now, one thing, of course, so it's going to divide the U and V values equally. And it might be slightly frozen for me right now. So it's just going to stretch out the boxes in this direction. So it's not going to add more to the fact that this has a longer side now. But we can easily make some interesting structures here. So next thing we want to do, and really what you have to do to finish this thing out, is just do a simple pipe to make this into solid geometry, which I haven't done this yet because as soon as I do this, it's going to go from being a fairly quick moving definition, and it's going to be slow. So I need to put in a value for the radius. It's going to see what 2 looks like. And there we go. So that could be it. I'm now going to go over the optional portion of this definition, which is adding in this stuff here, which will give you color if you're interested in it. So first thing I'm going to do is I no longer need to maintain all the graphing that was here. So I'm actually just going to flatten this to keep it simple. So just right click and flatten. Now, every time you do any change, the pipe command is going to rerun. So I'm just going to disable this so that it can be fast again. So in order to apply color, and the way I did it was I applied it based on length. So I need to figure out the lengths. So feeding this in here will give me a list of just lengths. I now need to do the same thing that I've done for a lot of these, which is I need to remap all this data from 0 to 1 so that I have a consistent set of data to manipulate. So I need to do the bounds. And again, this is exactly the same thing. I end up using this same process for a lot of different definitions that I write. But then I need to do a construct domain, a 0, a 1. So feed this in, feed that value in, and then I need to remap. So our data is going to be the length, so we're going to feed that in there. Our bounds is going to be the S, and our target domain is going to be this 0 to 1 domain that we created right here. Now we're going to do the graph mapper. That way we can do some interesting things with this, and I will just do the standard power graph. Feed our data in there. And then I'm going to need another bounds. And this time we're going to pull out a color gradient, which is, what's this one actually called? Just called gradient. So that's actually on the params. This guy here. So the default gradient is going to be this sort of red to, or pinkish to red. If you click on any of these values, I believe you can adjust them. So we could say, make this into, how about blue? Ooh, that is not what I thought it was going to do. So I guess anything below 17 or 30% or whatever this is now just completely one color, and it's not fading between. So there are, I'm going to exit out of this. Sorry, I thought this did something slightly different, but we can go to presets. So I'm just going to stick with presets because that's going to be easier. The one I did here was sort of red to yellow to blue. You can also do a full rainbow preset, or this sort of green to yellow to red, or any of them here. I'm going to do the green to yellow to red just because it's not what I did last time. So it's looking for a couple things. So let's see what I did here. So we need to deconstruct a domain. I think it's this one. So unlike constructing a domain, it just deconstructs it. So it brings us down to a start value and an end value. So we're going to plug that in. And or do we actually need to plug? Looks like the way I did it last time was take the bounds, plug that guy into there, that guy into there, start into the, sorry, I wish I could say I remembered how to do this, but I did this one late at night, so I have to see what I did last time. So start value goes in here, E value goes in there, and it looks like the T value is this guy. And now we can do I believe this is a custom preview, which we'll find under display, or we can just type in custom preview. And essentially it's asking for the material and the geometry. So our material is going to be our color, and our geometry is actually going to be these pipes. Now the pipes are currently turned off, so it's not going to display anything. And the other thing I'm going to do is actually select everything and now disable the preview. The reason being, this will only preview when you actually have the selection turned off. So if we now enable our pipe, which always will take a second to process, it should hopefully not crash. So it nearly crashed on me, and I figured out why. And this is always the reason why Grasshopper will nearly crash on you, which is that you don't generally want to mix grafted data, which is this dashed line here, with ungrafted data, which are these smooth lines. So because I am pulling in grafted data with ungrafted data, I am ending up with a preview that's trying to show 76,176 individual components, which is not correct because it's just not working. So I just need to flatten this, and it will solve everything. So theoretically, we should have color now, and we do. So our longest pieces of material are going to be the red ones there. It looks like actually we have a fairly even distribution on the vertical members, and our shortest are going to be on the inside of that curve. So that's interesting. I think, can we bake this? We'll keep its color. I'm not sure. Nope, it doesn't look like it. Looks like that's only for display purposes. Oh wait, no. They do have color to them. Oh no, that's just because we're seeing the rhino or the grasshopper. Anyways, so that's a space frame. So once you are happy with your space frame, whether colored or not, I'm actually just going to pull this guy aside since that's the baked version, and I'll show my lovely colored version next to it. So this would be my screenshot. Well, at least for the rhino side, and then we'll get this set up. So again, you wouldn't want to show both of those because you only have one. It's more important to see this side because that's the one that you should focus on. But if you can get them all in, again, I would probably need to condense this to fit it all on one page. We want to be able to still see the components. So if you zoom out too far, you can see they just kind of turn to black bars. But zoom in enough so we can see the names. That's going to be helpful. So if you can't fit the whole thing, at least fit this side. But that's going to be it for this demo. So again, the real challenge with this one is really just keeping organized because you have a lot more pieces. All the pieces themselves are fairly simple. I mean, we have lines, polylines, and we're flipping some data around. And it's just because, when we're organizing this, the way it works is, it's going to organize things by rows or columns, and then we'll just have to flip that to get the opposite. So that should be about it. Good luck with this one, and I will make the final video, which is the optional how to do a sort of 2D paneling later tonight. But that's it. Thanks.